couple of things in the last session I could have talked about. There's no way I can give you like a complete picture of Gaussian processes. If I were to do that, we'd be here all week. You've got to be here all week, but I don't have to be, so no, we can't do that. What I thought I'd do is I have this little thing on Kalman filters. Who here is familiar with Kalman filters? Yeah, so you can do like entire graduate courses on Kalman filters, I believe, which I've never done. So I've not actually done a course on Kalman filters. And actually, I'm not going to present the most general form of Kalman filter, but I'm just going to sort of construct a Gaussian process from a Kalman filter as a way of leading into multiple output processes. And then if I've got time, I might talk a little bit about dimensionality reduction. Actually, I got into Gaussian processes entirely because of dimensionality reduction. So that was sort of my main interest. I wanted to use them as an approach to doing dimensionality reduction. But I always feel a little bit like, you know, you shouldn't present too much of your own stuff at summer schools because, you know, you're not sure if you're just blowing your own trumpet or actually teaching something useful. So let's start with the sort of Markov chains. So Markov chains is something you should be familiar with. It's that thing that Laplace talked about, that the state of the universe is the cause of that follows and the effect of that precedes it. So if we have the state of the universe xi, what we say is that it's given by xi minus 1 plus some corruption. We could make it a more complex relationship between the states, but that keeps it nice and simple. So the state of the universe today at time I, this is discrete time, is given by the state of the universe yesterday, at day I minus 1, plus some corruption. Now, the corruption, if we assume it to be Gaussian, then this is how we approach a sort of Kalman filter or Gauss Markov. It's known as a Gauss Markov process because it's both Markovian and Gaussian. And that tells us that, where's the pointer? Here we go. That tells us then that the state today is given by something with a mean of the state yesterday plus alpha. So I'm just going to assume a 1D state for the moment. We can extend that later, but for the moment we'll just assume that the state we're interested in is one-dimensional. And now the Gaussian process is specified by a mean and a covariance function. We've kind of not talked at all about the mean. It's just a general. It can be any function you like, the mean. It's not special. The covariance function is special because it has to be a positive definite function. Whereas a Markov process is defined by its transition, and this is the transition between states, and its initial state. So we need to sort of say what happened sort of when time began. Obviously, God sampled from a Gaussian to determine the initial state. The initial state of the universe, or whatever the system we're looking at, is Gaussian sample. Then we have a sort of Markov chain for all these latent states, but it's specified by conditional distributions, you know, the conditioning on one given the other, rather than directly by a joint distribution. So what we're going to do is we're going to go from that conditional specification to a Gaussian process covariance. We're going to try and compute what the covariance associated with this process is. Now, I think that that's an interesting exercise because I think this is quite intuitive. You know, what's going on, that this is my system, that it's going from this state to this state in this way. I think you get a handle on that. And actually, probably when you see the covariance function, you won't find that intuitive at all. So it backs up this point that covariance isn't the only way of representing the process. It's not always the most intuitive way. But the nice thing about it is it allows that process to be combined with other processes easily. So here's my little visualization of, actually, did you have that pointy clicky thing? Yeah. That would be cool. Oh yes, it's here. I just can't see properly.
Yeah, you just have to...
Yeah, no, it will actually fit in. This is a very convenient laptop with one port, and it won't accept, yeah, look at that. You see, it's such an elegant design that you can't actually shove that in. There we go, look. So I'm just breaking all the connections by doing that. Okay, so... there we go. So what we're saying is this. Actually, I'm going to assume the initial state is 0 here. I'm not sampling from a Gaussian for the initial state. I'm just taking it to be 0. And then what I'm doing is I'm showing how a process such as this could evolve. So in each case, I'm sampling, as I go forward in time, a new Gaussian variable and adding it to the previous state, and I sort of just get a path like this. Okay? So that's clear? Now, what I want to do is I want to find out what the covariance function is for that. And again, this is the beauty of Gaussian processes, that you only need to know this rule. I mean, here I've added the plus b onto the rule. And also, I suppose, the rule that if we corrupt it by adding noise, then Gaussian noise, then that covariance would also be additive here. And that really allows us, this is pretty much all we need and a little bit of thought to derive the covariance function for that process. Because if what you can see we're doing is we're actually adding Gaussian random variables to a state. So what we need to do is work out how the state is dependent on something that is in the form of a matrix multiplied by something we know the covariance of. And that'll turn out to be quite easy to do. So let's have a look at how we do that. So what we can see from the way I've defined things is that if we start at 0, which is why I've started at 0, x1 is given by epsilon 1, the corruption on day 1. x2 is given by x1, which is just the corruption on epsilon 1 plus epsilon 2. So on and so forth. x3 is given by the sum of these three noises. Because if we start at 0, it's just the sum of the noises we've seen so far. So actually, you can immediately see that the state of the system is given by this lower triangular matrix of 1s, sort of multiplying like that. That gives us the effect we want. And of course, this we've defined to be a unit covariance Gaussian. So this epsilon is just the corruption noise at each step, and the W matrix from the equations before is now L1. So we can immediately sort of write down the, actually I don't need to go through that because I don't really use that bit anymore. I keep forgetting to take those slides out. We can immediately write this down. If x is given by L1e, so what I mean L1, why I've used that notation, I'm not using it as an index, it's a lower triangular matrix of 1s. And epsilon is given by this process here, sampled from Gaussian with alpha I, then the process for x has this form. This is what it looks like as a Gaussian process. Discrete time process, right? There's no notion of continuous time in here. But this can be built up in a discrete time way, that x is given by a Gaussian with 0 mean, because the mean of here is 0, and alpha, this scale here, well, so this would be created by L1 alpha I, L1 transpose, and then we just bring the alpha out the front. Okay, is that clear? So that's the covariance function for a Gauss-Markov chain. Now, we need to make that continuous. And the way we're going to make that continuous is we're going to just sort of assume, and this is actually the only sensible assumption, that the variance grows linearly with time in the process. So that over time, the variance is going up. That has to be the case because the sum of two Gaussians is also distributed as a Gaussian with the sum of variances. So if we're adding incremental amounts of variance in discrete time intervals, then the additive things has to occur on the variance. So if I just sort of assume that the variable's variance is additive over time, then what I'm going to do is rewrite things in this way. So I'm going to say that instead of daily intervals, we have a delta t, which is a part time interval. Okay? So we're going to do that usual trick of taking delta t down to 0 to make it continuous time. And I'm going to say, well, if it's only half a day, then instead of adding alpha worth of variance, we'll add half alpha. So the actual thing we add is now dependent on the time interval. So if it's 1 day, we're adding alpha, but if it's half a day, we're adding half an alpha, and if it's 2 days, we're adding 2 alphas. And that's the only thing that makes sense consistently, because that is true regardless, you can't, because of the way Gaussians add, you have to do it in that way. Now, once you've done that, you can now write down that the covariance function has this form. So, of course, that delta t just follows the alpha round, so the kernel in this case has this form. But let's look at just an element of that covariance function, so the ith row and the jth column of that covariance function, giving us the correlation between the ith and jth time point. Well, it now has this form, which is this is a column from this is a vector from the ith row of L1. So and then this is a vector from the jth row of L1. Now, because that's a lower triangular matrix, the first k elements of that vector are 1, and the next t minus k are 0. So that means when you take this inner product, you've got an inner product between. So you get two vectors of the form, so 1, 1, 0, 0, 0, and then maybe you have another vector of the form 1, 1, 1, 0, 0. If this was the second row, it would have two 1s because it's a lower triangular, and if this is the third row, it would have three 1s. So when you take the inner product between these two, you find you just get the minimum. This would obviously come out as 2, which is just the minimum of I and j. So however you do this inner product, the answer to this inner product is always simply the minimum of I and j, because everything else is always zeroed out by the other vector. So you have these vectors that you're taking inner products between, which have as many elements as the row they're from, so the last element has all of them. But when it multiplies by something from the second row, these three elements get multiplied by 0, so the sum of all of them is just the minimum of I and j. So you can replace the, that inner product with this, minimum I and j. But now we notice that we can actually pull the delta t through the minimum of I and j. This is either going to be delta ti or delta tj. So this is just the minimum of delta ti or delta tj. But delta t times I is simply the time at the current point, because that's our defined time interval. So we can simply replace this as the covariance between these two is the minimum of ti and tj. So that's the covariance function, a pretty weird covariance function. I think when you wouldn't actually, well, maybe, I don't know, I mean, who would guess that that's positive definite? But anyway, it is. It's positive semi-definite, I guess. And this is the covariance function here. It's positive semi-definite because I think we have to take the prior over the initial state. We can't set the initial state to 0, I'd suspect. So this is the form of the covariance function. I haven't checked that, but I'm just thinking on my feet there. And this is what it looks like. So this is time 0. We haven't defined how we go backwards in time here. But this is time 0. And at time 0, we define things with 0. So actually, you see everything is sort of shut down. And then over time here, what we get is something that goes up linearly. Now, this is actually a proof. So what we're describing is a particular type of process that was discovered a long time ago. Who discovered, or who, I don't know, who discovered this process? Well, I don't know, who proved the things about this process? What process is this? Yeah, so I would think of it as a Brownian motion, yeah. But, it's Einstein sort of did a lot of work on Brownian motion. The person who observed it was Brown.
No, it seems that Bachelier was the first when he was three-dimensional mathematics.
Well, I think that's one of the fascinating things about academia is like there's always these narratives of who was the first and who did things, and you can read it on, if you want to check it out, you can just read all the stuff on deep learning at the moment. And actually the truth is communities and people just did stuff, but you know, it's that very old process of something that just bounces around. And well, I don't know, the person who observed it supposedly was this pollen moving under a microscope, and it was moving around because it's getting hit. And the idea is it's getting hit by little Gaussian hits over time. But this is the continuous time variant of the discrete Gauss-Markov chain. And it's a Markov process. Now, what do we notice about it? For example, immediately you can tell that since this is the minimum of t and t prime, that the diagonal is just the time. So what does that mean for the variance over time? It's going up what? Linearly. And that means, of course, that the standard deviation is going up as the square root over time, which is a known property of these random walks. And this is what it looks like. So this is interesting because these Gauss-Markov processes, they always have these, they don't have derivatives. They don't have a first derivative. They're continuous but non-differentiable. Now, when you see Kalman filter smoothing plots, you will never see things that are done, that you won't see these non-differentiable paths. Why is that? They never show this. What do they actually show instead that looks smooth? So it's a Kalman smoother, right? So it almost looks smooth. So what do they show? They'll actually always show you like, a particular thing that we've seen a lot before that you will never see sampled from this process. I've talked about that before. Someone? If you're plotting this, if you were plotting like your posterior belief about where an object moved according to a tracker, what would you plot? The mean function, yeah. And the mean function is smooth. Well, it's discontinuous at the points of, but it looks like a straight line. It sort of seems to smooth things. Piecewise, yes, piecewise continuous, yeah. But it doesn't look like these. And it's a really good example of something where the mean function looks nothing like the actual underlying process. So that's the nature of that process. Now, here's a really cool thing. Write down this covariance function. Exercise for those of you, whichever programming language you use. Just write down 0 to t, and then compute the minimum, compute the associated matrix that's the covariance function. And then invert it. What will you see when you invert it? Can anyone tell me? There's a special property of the inverse that you know, by the way I've constructed it, it must be the case, but it's still kind of shocking when you do it. Tridiagonal, yeah. That's what the inverse looks like. It's a tridiagonal matrix. And this is kind of a bit freaky because you write down this matrix and you do the inverse. Of course, you know by construction that this has to be the case. But all these things off diagonal are 0 because this is representing the conditional dependencies in the Gaussian. So the covariance represents the correlations, but a very different thing, so-called partial correlation sometimes, is the conditional independencies. And this will always show you the structure of that graph. So this is showing you that there's a chain structure between all these variables. That's what the tridiagonal matrix means. You know, if there was an off-diagonal point here, it would say, and then there's also a loop going around like that, if that was a non-zero element here as well. So that is a particular, you know, and that's very rare. In Gaussian processes in general, you don't see that. That's unique to these sort of Gauss-Markov processes. And also, I don't think you can do it in more than one dimension. I'd like to. That's when it gets confusing how you do this in more than one dimension. But certainly this, to my knowledge, only really works in one dimension. If we do the same operation to this process here, I have slight color blindness, and this color map really freaks my eyes out. Am I the only one whose eyes are freaked out by? But anyway, this is the same thing. This is the inverse of this exponentiated quadratic. Now you can show, interestingly, this thing turns out to be infinitely differentiable. And that implies that it also is infinite order Markov. You can't represent it as a Markov. You'd have to have an infinite state vector in order to represent it as a Markov chain. And well, numerically, I'm pointing it there. I don't know, I'm pointing there. Actually, so this means that all these things are, in theory, non-zero. Of course, numerically, they appear as 0. But you see this sort of quite, I don't know how to interpret that pattern, but it's certainly not. You see some like, yes, there's a strong dependence on the time point before. That's the strongest, and it weakens as you go out. Compare that to the, yeah, you see, there's no structure out here. So the smoothness is actually brought about by having that higher order Markovian structure in order to get the differentiability. So now what I want to do is take that Markov chain and turn it, that's not a Kalman filter. So a Kalman filter is that model where there's an emission at every state. Now, so that emission at every state is what I want to look at now. And again, it's a simplified version. This is a specific variant of the Kalman filter. What I'm going to do is I'm going to assume that I've got latent states. So I've got multiple latent states, so I should be drawing like that. They're doing this 1, 2, 3, 4, 5, whatever. And then what I observe is related to that latent states by an affine transformation. So my mission is take those latent states, multiply by matrix W. So if I have a two-dimensional latent space, I can be expanding it up to see a high-dimensional observed space. And I might even corrupt this with noise. That's easy to do, but for the moment, we'll just assume it's Wx like that. But what I also want to assume is across, I'm going to have Q of these latent spaces. I'm going to assume they're independent. So I've got Q independent latent spaces. So, and each of those latent states, and each of those latent states is given by the same, they've got identical covariance functions. So they're all coming to this Gauss-Markov covariance function, but they are independent. So the overall covariance function for them would be block diagonal. And block diagonality can be written just as a product of the different Gaussians, obviously. But this means I have to do a little bit of a weird operation, because I can't now, what I've been showing you before, like it appears I'm in a good position to now tell you the overall covariance function, and I sort of, in theory I am, apart from this W matrix multiplication is working across independent x's, which are correlated through time. So we now have a sort of Q latent things, and then W is going to map it out to a p-dimensional thing that you observe. So W is a p by Q matrix. But I've got various dimensionalities. I've got time, t-dimensional, q-dimensional, p-dimensional. So when I'm in this sort of situation, the matrices get a bit confusing to think about, and what we actually move to is Kronecker products. So I'm just going to quickly review sort of Kronecker notation for doing this, because it's really useful for these. This will turn out to be a multi-output system. And in some sense, Kronecker gives you special cases of, it's a way of adding structure to a covariance where you have types of things like you've got p-dimensional outputs and t-dimensional times. It's a way of writing that structure in this way that everything looks still like a matrix. So what we do is actually, we typically, to deal with these multiple output systems, first of all, we never really want to, it's the most general thing is not to talk about, there's things called matrix variate normal distributions, where you put a covariance function over a matrix. So you say, this is my matrix, and I'm describing a covariance function of this. That's a really restricted case. The general case is to do something else, to just say, I'm never going to talk about matrices, I'm always going to talk about vectors. I'm always going to talk about correlations between vectors. So if we want this system, this one I've talked about here with multiple independent processes, the way to deal with it, to talk about full covariances between things, is to stack the system. So you take the sort of, we've got this design matrix of X, which is q-dimensional here, and has t time points. And then this is each of these is drawn from a Gauss-Markov chain, or the Gauss-Markov process. And then what we're going to talk about now, I'm going to re-represent that using Kronecker products as one vector which stacks each of these like this. That's the typical way we do it. So that's our new vector x, which is just the stacked version of our matrix x defined here. And then we can use this Kronecker notation to represent the covariance. And all this Kronecker notation says, in this case, it's just making a block diagonal covariance k. So if you've not seen, who here has seen Kronecker products before? Okay, so some of you, but not everyone. But here's a Kronecker product on k, and all it does is it tiles k and scales it. So it's a tiling and scaling type thing. So visually, if you have some structure like this, you just get this structure repeated, but with different weights. So if this is like A, B, C, D, and we're weighting each of these things, I've made it symmetric, so it looks like a covariance matrix. We see something like that. And so in this case, of course, we've just tiled it along the diagonal because we're Kroneckering by matrix I. So that looks like that. So this is our individual k's, and this is our vector x. So when we look at this, if we were to look at any individual marginal distribution, we would get the marginal distribution over time. And that's actually not what I want to play with, because I need to multiply this by that matrix W in some way to give me the output Y. So this is the covariance function over X, but what we actually want to operate on is we want to look at the covariance function for Y, and Y will be the thing we observe. These are X latent functions in the Kalman filter. So that's the marginal distribution for any one of those Markov chains. But what I really want to do is I want to take an individual time point, the values from that time point, and multiply those out to see things. And it's actually quite easy to do that by flipping things around. So I've defined things by stacking the columns here, but if you were to stack the rows, so if I just say, well, X is formed by row stacking, then all you do is you flip the Kronecker around. So this is the covariance function for the row stacked. Effectively, that's a reordering, and that reordering is just represented by this. So if we Kronecker that by that, we get this instead. Now, if you look at the marginals of this distribution, That is the marginal distribution for one latent vector. So Q-dimensional latent vector. So they're, of course, all independent because those chains were independent. And this is the object, this is the actual thing you want to multiply by W to get the new covariance. So what I'm trying to persuade you and trying to make intuitive is that this is the right thing to do. So if we're going to say Y is now given by multiplying an individual time step I, the entire Q-dimensional vector of it by W, and then corrupting it by noise, that this is actually the thing we want to do. We want to row stack instead of column stacking. By standard, we normally column stack, but we want to row stack those vectors and then multiply it by this matrix here. So now this is multiplying the first row stacked vector, the second row stacked vector, the third row stacked vector, to give us this thing here, which if we corrupt by epsilon will be Y. So we get Y in that way. So now, all I have is this Kronecker form, a form I Kronecker W, K Kronecker I, because I've had to flip that back the other way around, I Kronecker W plus I sigma squared. So Kronecker products have these rules. If this is two products like this, you can replace that with AC Kronecker BD. And if you just apply those rules a couple of times, you find you get this structure here, K Kronecker WW transpose plus I sigma squared. So this matrix is our original Gauss-Markov process covariance, the minimum of TT prime. And this matrix is just WW transpose. It's a low-rank matrix that is P by P and rank Q. And then, of course, we corrupted things by noise, so we get a noise out like that. So this tells us that for this simple variant of the Kalman filter, this is the covariance function. WW transpose Kronecker K. Now, why would we not want to use this covariance function in practice? Well, if you just write that covariance function down and you don't start applying tricks, then you've got to invert this whole matrix in order to do Gaussian process inference. There's a few different tricks you can apply to actually even make this structure quicker to invert. But that is going to be, this is a P by P, this is an N by N. So this overall matrix is a Pn by Pn. So inverting it is going to be order Pn all cubed. So the output dimensionality times the number of data points cubed. That's the worst case complexity. And this is a difficulty for when you're doing with multiple output processes. You get this severe cubic complexity. Kalman filters are all about algorithms that allow you to do that inversion efficiently in a sort of a linear time and I think quadratic in the number of latent chains you have, as number of independent or then often not independent latent chains you have, and exploiting that inverse structure that's tridiagonal. So this is the separation between model and algorithm that I mentioned in the beginning. Like, knowing this and being able to write this down can still be useful because you may want to know a priori or you may want to combine this with something else. So understanding that that's the model you're fitting is useful. But algorithmically, you don't normally fit a Kalman filter in this way. So how could it be useful to do this? Well, I'll try and give you some intuition of that because I'm trying to use that to not just introduce Kalman filters, but also introduce an approach to doing multiple output processes, which is the sort of thing I mentioned at the beginning, where you just Kronecker product the correlation between your outputs and another covariance function to give you a larger covariance function. It's like the simplest way of doing it, and it's known as the intrinsic model of co-regionalization. So Lorenzo Rosasco is like a kernel guy, and it's like some years ago, I think about 8 years ago, Maurizio was a PhD student of mine, who's now assistant professor, associate professor in Columbia, and Maurizio did most of the work. Did this review of kernels for vector-valued functions. This is a big area. Trying to relate what people have been talking about in kernel methods to what people talk about in Gaussian processes and to an area known as Kriging. So there's an entire field known as Kriging that's been around for a long time that is just sort of Gaussian processes, and they do multiple output things there. And this tries to review these different methods. And this is the core object of the main thing that we review in that paper. We were actually doing something else. We were doing something called convolutional processes, but we were trying to compare it to what everyone else had done. So we certainly didn't do anything to invent this. But what does that mean? Well, this is that Kronecker structure I talked about at the beginning. So people like, I think that this notation is so confusing and complicated. It's sort of saying, well, what we now have is a matrix. So this is for vector-valued outputs. So then people talk about things like, okay, so my kernel function should generate a matrix for every 2 inputs because I'm doing a vector-valued output. Which is kind of true, but at the same time, it looks a lot more complicated, and actually it's just doing this thing on the right. It's just a particular covariance function, like I said before, where you take 2 inputs. One is your x and your x prime, then you multiply by another covariance function, which is a function of 2 indices, j and j prime. I could have said I and j, chosen j and j prime, which is the correlation between the 2 outputs you're interested in. Why is that? Well, because if we look in this case here, we can actually rewrite this object here as B Kronecker K. So WW transpose, and this is known, in geostats, this was known as the co-regionalization matrix, because it's about like how co-localized outputs work together. So this matrix B is a co-regionalization matrix. So this is the matrix form, but actually it's even simpler to think about it in the covariance function form. So the thing we're looking at is, see if writing on here works. All this would say is k of x comma x prime times bij. Sorry, j prime. That's what this says. So what you're sort of saying here, is this thing here. It's a kernel function, but it's a kernel function that is has a finite domain of countable indices, which is known as a matrix. So it's a covariance function, but it's a covariance matrix. So it's just a special type of covariance function. So you're just saying that all this object tells you to do is multiply your original covariance function by elements from a positive definite matrix, has to be, with indices j and j prime. Yeah? Not very complicated. It's like the simplest thing you might think of doing if you were aware that this also led to a positive definite matrix over things. But it also has this interpretation of what you're actually saying is the system I'm looking at is really the result of several independent systems that have then been linearly linked together by actually the eigendecomposition of B. That's one way of looking at it. There's a bunch of other ways of looking at it too. Once you realize this matrix B is just a positive definite matrix, you can specify it in other different ways. And a common way to do it, a cool thing to do, is to actually say that this is sparse inverse. So if you're relating tasks, you make this a sparse inverse, which in effect is specifying conditional independencies between things you think are related. We actually haven't implemented that in GPy, and I keep thinking, should implement that in GPy. But this other model is easily implemented in GPy. So that's very much in our software. This is the way we tend to think about things. That a multiple output thing is just a particular, well, it's just the same. The most general thing, ironically, is a single output thing. Now, there are special cases because you can actually invert these things more efficiently if you know you have this structure of covariance matrix. But the most general thing you can do is actually single output, and all you're saying is you've got this situation. Look at that. I even knew what I was going to write on the next slide. So B is this co-regionalization matrix. Now, we call this class of covariance functions separable because they separate over these 2 parts, x and j. And actually, they're fairly simple, and they have some particular problems. But what's really quite cool is you realize that you can immediately extend them. Now, you can't do this with Kalman filters. It doesn't lead to anything interesting because adding multiple Kalman filters together just gives you something that looks like a Kalman filter. But here's an extension of this model where you actually have different covariance functions being multiplied by this B. And this would look like this. So this would be like several Kalman filters. So imagine like you've got Kalman filters and then you're adding different Kalman filters together. Well, you know that adding the output of those Kalman filters together must lead to another Gaussian process because adding Gaussian processes together leads to another Gaussian process. It just happens in the Kalman filter case, it's pointless because adding these Gauss-Markov processes together just necessarily leads to another Gauss-Markov process. It just leads you to another Kalman filter. But what we can do in general is we can define different covariance functions with different co-regionalization matrices. So this is where things start to get interesting. And I mean, this this class of covariance functions is more powerful than you can possibly imagine. Sorry, I'm just quoting Star Wars there. But the reason is, it seems simple that you're just multiplying things on the output, but in these latent functions, you can start doing interesting stuff. So you can say, I've got maybe 5 smoothly varying at this length scale covariance functions, and then I have some rapidly varying covariance functions, and I'm going to co-regionalize these with different matrices. And then when you look at the samples you get, that starts to get quite difficult to interpret what's going on and what the length scales are. And rapidly the number of parameters go up, and then you end up with very powerful classes of covariance functions. They become harder to interpret and harder to fit. So we had this realization because Maurizio and his thesis was on these things called latent force models, which are actually multiple output covariance functions derived from mechanistic models, differential equations. And we were like, cool, they're really complicated and difficult to compute, and we'll easily be able to beat this class of covariance functions, which is much more restricted. But Maurizio was a particularly good PhD student, so rather than just running the first test, he actually implemented all this properly and found that this class of covariance functions was difficult to beat in the sort of domains where we thought we would win through. Where we won through is our objective was to build covariance functions that extrapolated better, and we did beat them in that domain. But just in terms of interpolation, they do very complex things. So these multiple output sort of GPs were pioneered, as I said, in geostatistics. This model of covariance functions of summing several of these things up, so instead of doing a Gauss-Markov chain as your latent process, you're just doing any Gaussian process covariance function you like, your favorite one. It's called the linear model of co-regionalization. And it has computational difficulty, it's quite, you have to, for large systems, you have to start approximating to fit it. But it's been around sort of since 1978 in that literature. It's not so easy to always read that literature if you're used to machine learning ways of describing things, but Maurizio did a really nice job of translating those ideas into this paper. So in machine learning, people have said that this is multitask learning with GPs. I personally don't really like that term because multitask is a bit of a vague term. It's this idea of I can learn one task and relate it to another, and there's like a million number of ways you might do it. And I think of this as more as multi-outputs. It's one way you could treat multitask. So the idea in this paper, this is by Chris Williams, Edwin Bonilla, and others, is that you have now these multiple outputs of related tasks, and this matrix is now giving you the correlation between those tasks. And it's a way of doing multitask learning, but it's certainly not the only way you could do multitask learning with GPs. So these are sort of weighted linear sums of different latent functions. And we've already so I've sort of reviewed that the Kalman filter is this specific case where this latent thing is a Gauss-Markov process. But in general, for co-regionalization, and certainly in geostatistics, that's all about spatial processes. So it's used a lot in mining or understanding how minerals are distributed over space. It's used a lot. Actually, this is fascinating. I watched a thing, I only watched the first half of it, I haven't got back to it. There was a thing on the BBC which involved David Spiegelhalter and various other people talking about the mathematical models behind climate science. So, what people are doing in climate science, because there's these scandals, they're manipulating their data. There's this university in England where they wouldn't give up their data, and people are pre-processing their data in different ways. And the whole premise was based on, point number one was that they've got the sea surface temperature record that comes from throwing buckets out of a ship and pulling the bucket in and measuring the temperature. And apparently, during the Second World War, people were unwilling to go out on deck and throw buckets in. So they just sat inside the ship and got some water from the engine room, which was somewhat warmer than the water from the sea. So there's this big jump in the sea surface temperature record in the Second World War. And apparently also, depending on whether you use a canvas bucket or a wooden bucket, you get a different thing. So, and they're sort of saying this, they're going through all this in a nice historical way, looking at these buckets, and all these sort of things. And then they sort of say, so how do we do that? And then they have these wonderful BBC graphics, visualization. And anyway, so to deal with this discrete change, they used a Kalman filter model, which I thought, okay, right, fair enough. So they're saying they're Kalman filtering the sea surface temperature record. Now, the next thing was, okay, that there's problems because you can't get ice cores everywhere, so you don't know the historic temperature record. I'm not a climate skeptic, by the way, but after I watched this thing, I was like, oh, Christ. Then they're doing these ice cores, and these are serious people that sort of think that this is okay. I don't know if I think it's okay. They're doing these ice cores, and they're trying to work out spatial temperatures based on point measurements. And then they sort of had this whole thing of standing around with poles and talking about Krieger, this South African mining engineer who worked out how to spatially smooth these things. And then they said, we're spatially smoothing this record at every data point for the whole Earth. And I'm thinking, you've just built a Gaussian process over the spatiotemporal record of our temperature. And the fantastic thing is they're consistently saying when they're doing this, oh, this isn't making assumptions. This is just the right way of handling the data. And that's the idiocy of looking at the algorithm and not the model. These are serious people saying that. You have made a joint Gaussian process, spatiotemporal model assumption over what the temperature record is across the globe. And you haven't even then fitted it jointly. That would be a right pain. You know, there's good reasons for why you might want to fit that jointly, because there's quite a lot of bloody large data. And you could write down the covariance function, the precise covariance function for how they're modeling it. And then this thing, once that comes out, that's what goes into climate models. You know, so it's been modeled already once by something that is just a spatiotemporal Gaussian process, but ignorance of where the model is, and assumption that these algorithms are correct, and lack of understanding of how they generalize, has led to these. Well, you know, the whole premise of the film was at the beginning, we're just mathematicians. We don't care about the actual data. They were walking along, that's why I'm doing this, sort of across a bridge in Westminster. And I was thinking, oh, this could be interesting. And then, you know, I had to go to work. But I'm going, Dad, you can't say that. I still believe in climate change. But I think that that's a really interesting example of the way that we should, you know, there's the way we do model, which is like, okay, we're going to smooth this data. You know, fundamentally, this happens all the time. I had a project with a student who, it's a cycling-based project. What we're trying to do is understand what your tuck position is by reading power and reading your altitude and seeing what your speed is, because it's all like force balance, and using Gaussian processes to infer missing things. And we had a challenge in that because we had this altimeter with a wind meter that was a static one, so it's designed for holding like this, and we strapped it to the front of his bike to get the wind speed. And everything worked well, apart from we didn't have a power meter, so we just had him going down a hill, and so we could work out the power. Power meters are expensive. But then there's a bump in the hill like that. And then he's got this nice video of it all working, showing not an accurate coefficient of drag, but showing whether he's sitting up or sitting down, until he hits the bump in the road, when it immediately thinks he's sat up. And we had to look at it, and you end up realizing, well, that's because that we're using the barometric pressure from this wind meter, right, in order to estimate altitude, because it was more sensitive than the other altitude sensor we had. But that's designed to be held statically. So, of course, inside that sensor, there's some smoothing going on. There's some sort of, we don't need to, so someone's put a little Gaussian process in effect on that sensor. We're not allowed to see the actual reading, so what we actually see is a smooth version of the reading. And when you start trying to pull sensors together, and in this case we're using the sensor for the wrong thing, it's designed for someone to stand there, not go rapidly down a bump. But you realize how much processing is being done that implicitly itself is a Gaussian process, and then you're actually seeing the smoothed output of that. Same for climate models as well. Now, in the real world, that's fine. I mean, practically, I'm not going to sort of phone up the manufacturer saying, can you take your filters off your barometric pressure, because we'd like to handle that bit ourselves, which is what we'd really like to do. Put that in the covariance function properly and assimilate it with other pieces of information, because that would be the right way of doing it. But no sensor manufacturer is going to do that. They're always going to do a little bit of filtering on their and which means that you're seeing some sort of Kalman filtered variant. Now that's okay, but you should understand that's what's going on when you're building your model, and understand what the right impractical thing to do and how you can't do it. Okay, so yeah, so here's some samples from this. So actually there's a few different models in machine learning that, so the Kalman filter type one is called the intrinsic co-regionalization model. That's what its name was originally, but in machine learning, we've renamed it multitask Gaussian processes. But it has this weird problem that actually you can just independently fit B and K. So actually that thing that they're doing temporally and spatially with Kriging and time is all right but only if you collect the data in certain ways. It's not all right the way that they're doing it, but it's some sort of approximation. So this independent fitting phenomenon is known as autocreatability. Hans Wackernagel, who's really good, he does a lot of Kalman filtered, extended Kalman filter work now. He's based in École de Mines, Paris, and a very interesting person to hear talk, and just comes from this geostats background. His supervisor was Materon, and Materon did all the sort of formalization of Creechy's work, and there's a large body of French work on that. And then in multitask learning, we called it, Edwin and Chris Williams, and there's another author whose name escapes me for the moment, called it the cancellation of intertask transfer. So this is the sort of what these intrinsic co-regionalization models look like. Here I've got a rank 1 system, so my W is a matrix, it's a vector, going from 1 dimension to 2 dimension, and so you should really be able to see very clearly what you get, right? So now I've got a Gaussian process. The latent process is not a Gauss-Markov, it's an RBF, exponentiated quadratic, as I call it. And this is the joint covariance, which is now just a scale. This is W. This is 1 times 1 times the original. This is 1 times 5 times the original. This is 5 squared times the original, so much larger. And if we look at the process, obviously, we just get the same process, identical, scaled by 5 and just scaled by 1. Because that's what we've said the model is when you think about the original model. I think it's not so obvious that that's what you're saying when you look at the covariance, but that's how we constructed that covariance. So there's a few samples, and that's all they do. Not very interesting. If you do a full rank matrix B, what you're now saying implicitly, although it looks like there's no sum here, but you could write this thing down as the sum of 2 rank 1 matrices, yeah? Adding them together, which implies that you've got 2 latent processes with the same covariance function driving this system. So W is now a 2 by 2 matrix. So although you seem to only have 1 process, that's because the statistics of adding 2 processes with the same covariance function comes out to the same process again. That's why adding Kalman filters together doesn't work, because that's always true that that's what happens with the Kalman filter. And so here's a full rank thing, and now things look a little bit more complicated. Like, this is not following exactly that, right? There's some differences. But actually, everything here is happening on the same length scale. So we can go more complicated again, and you can say, okay, so we're going to have 2 full rank matrices and 2 different length scale underlying processes. So now one is working at a long length scale, and the other is working at a short length scale. So the way these 2 outputs are correlating for these 2 different length scales is different. And of course, when you think about what that's going to look like, you can't quite imagine what that's going to look like. So it is more complicated. So, you know, is it clear a priori whether these things are correlated or not? I don't know. Of course, there's starting to be problems because we're starting to get a lot of parameters to fit here. So if you start to allow these general things to happen, you're building up in parameter space. I mean, here it's 2 by 2, but if you can imagine 10 outputs, the sort of thing we're interested in with these models is gene expression data, which is like 12 time points, 6,000 outputs. So now you're talking about co-regionalizing across 6,000 outputs. So in GPy, we always formulate this in a low-rank way to try and keep the parameters down. You don't need to. And we could actually write different covariance functions that allow you to do that in a different way. But you get these more complex interactions. I mean, so yeah, it looks like there's some correlation. Yeah, but you know, when's it occurring, when's it not? It just happens that that correlated process is now dominating, and over here it's not. So quite complex interaction on these. Now then there's a model called, so I'm just trying to remember what I've written here. Oh yeah, so there's various approaches that have been used for multi-output regression in machine learning, and they're often called multitask. I think I've already been through the fact that I don't like that. So I've dropped the reference here. But here's an interesting one that was from Yi Tay, Matthias Zager, and Mike Jordan back in 2005. And in this case, they constrained the co-regionalization matrices to be rank 1, but then had a process for each one. So this is somehow a simplification of the last thing. It's like, take this one, have many, many co-regionalization matrices, but each of them's rank 1. I think at the time they weren't aware of the co-regionalization matrices. So this is like a Kalman filter. This is almost like exactly like a Kalman filter, but now each of those independent processes has a different covariance function. So they can't be summed together into one thing anymore. And they suggest using a different exponentiated quadratic with different length scale across each of these. So this looks something like this, and then you get samples like this, which is still quite complex, but they've got less parameters. So you can see how something like this would scale, because you only have sort of q times m parameters, where m is your number of outputs being added in, whereas in the other one, sorry, q times p parameters, where p is the number of outputs, whereas in the other one you have order q times p squared parameters coming in. So these low rank forms are a way of sort of decreasing the parameterization. Okay. Okay, people have done it for classification. People do it for computer emulation, multiple output computer emulation, which I haven't talked about much. And I'm going to skip through. So this is a thing about Buchner's theorem, which is actually important, but I'm going to skip through it, which is another way of generating covariance matrices. So yeah, I've just shown you a way of generating a covariance matrix that I made up, actually. I mean, only using regular maths. Maybe someone's done it before. But I made it up for the purposes of educating what a multi-output GP is from Kalman filter, which I hope that some people would understand already. And of course, there's very many ways of generating covariance matrices. Buchner's theorem is another one. So Buchner's theorem tells us that if we have a positive measure in a Fourier space, its inverse Fourier transform, where we replace the time argument with the distance between two inputs, is always a covariance function, and it's a stationary covariance function. And each of these, this is an OU process. So this is actually a Gauss-Markov process that's stationary. So it's like that Brownian motion, but it's stationary. Like, it doesn't go off to infinity with a standard deviation of square root of time. These Matern 3/2, these are covariance functions that also can be created in that way, and this one is once differentiable only. So this is 0 times differentiable. This is once differentiable only. And then there's another covariance function called the Matern 5/2. These are very useful for low-dimensional problems, where this is twice differentiable. So it has the first two derivatives exist, but above that they don't exist. And they can all be formed using particular filters in Fourier space, which is another way of making these covariance functions. Ourselves, something we've done is base covariance functions on differential equations as well. So this one can be formed by a filter in Fourier space, and the filter used is a Gaussian filter. So, and that gives infinite differentiability, because it has support for very high frequency things. Okay, so I'm going to stop there and then just briefly say something about how I got into Gaussian processes. But let me take questions at that point about the multi-output GPs. Saturday morning, filled with questions, you know. Fun?
Everything is clear.
Everything is clear. It's clear in the front. Is it clear in the back? It's like everyone's nodding. No, no one's nodding. Yep. Yeah.
But how do you know it's not just a coincidence that the covariance is in that form? Like, what does that imply that there has to be two processes?
Well, it's one. No, you're right. It doesn't mean that that's what's going on. It's just an explanation that generates that covariance. There may be other ways you could generate that same covariance. So for example, this covariance, you can say, that's what happens when you get an infinite number of basis functions that are Gaussian form, and put them along the real line. Or you can say, no, that's what happens when you have some initial condition laid down as delta functions, and then the heat equation is the physical process, and then you get this form. Or you can say, no, that's what happens when you choose to filter things in the Fourier space with a Gaussian, and you only believe that, and then you get this form. So this form comes up a lot as many different explanations. And in the same way, the sort of thing you're saying is, well, how do you know that's true? Well, you don't. It's just one way of thinking about it that fits the end statistical facts. There could be other ways of thinking about it that fit those same facts. It doesn't mean that was the actual mechanism. It's just, it's one of those things the Gaussians are all about that, right? at the end of, I mean, not just Gaussian processes, but in general, at the end of the day, you observe something that is the sum of all sorts of other things, but it just emerges as looking like a Gaussian because of central limit effects. And this covariance function, ironically, because it has this weird Gaussian form, I know this wasn't your question, but it's worth pointing out, it turns out that a bunch of other processes converge towards this for the same reason that processes tend towards being, distributions tend towards being Gaussian. You don't know that that's what's underlying it. I'm just giving you one way of thinking about it. Other questions? I like to sort of have thoughts about what are plausible mechanistic explanations under my process, because I kind of don't really believe in the idea of a universal prior that works for everything. I kind of believe that these are, at the end of the day, they're manifestations of weak mechanisms that are occurring around us. And so this one is encoding smoothness. We've just given like 8 reasons why smoothness might occur. Not 8, but 3 or something. You know, I have trouble with counting because I like smooth systems. We've given 3 reasons why this sort of process might occur. So it's no surprise that this is like the go-to covariance matrix. A few different systems actually converge towards a process like this, but all this go-to covariance matrix is saying is things are smooth, infinitely smooth, too smooth actually. Okay, so in the last half hour, I'd just like to say something about dimensionality reduction. Yeah, no, good. Oh, yeah, great. So dimensionality reduction is actually how I got into Gaussian processes. So maybe this is more illustrative about if you didn't think that your problem was a Gaussian process, it still might be, because it may not be obvious why dimensionality reduction is actually Gaussian processes. So, we get these very high dimensional data sets, and obviously these spaces are very large, right? So this is a sample from independent model over that space, and it doesn't look like the digit, and you'll never see that digit. So the idea in nonlinear dimensionality reduction is that, well, actually a better way of thinking about the model would be to think that actually you've got some low-dimensional control space that generates the data. And I think this is a very persuasive idea. Certainly I did back in 1997 when it was first presented to me. And you can even show that this might be true. So if I take a digit 6 and I rotate it 360 times, each through a degree each time, and then this is just PCA on that data. And I was quite surprised when I did this that it actually really comes out as a pure circle. So this is a linear projection. As actually Chris Watkins said last night, he likes to think of PCA as a shadow, which I think is quite a nice thought. It is a shadow. So this is like a shadow of what's going on in that high dimensional space. And it happens to be a good shadow because you can see very clearly it's a spiral. And even if you look in other dimensions, you keep seeing this spiral shape. You never see much more than that. There's a little bit of noise around the spiral, and my intuition is that's induced because when you rotate digits, you have to, there's only 4 rotations that actually are noise-free. 90-degree notations because of pixels. The other ones you have to do some interpolation on the pixels, and that's why you get a little bit of departure away from the manifold. So the idea is that this is actually a way of thinking about data, that it lies on some nonlinear space in the high-dimensional space with little bits of noise corruption that pull it off the manifold, and that's a way of modeling data.
So what are your features?
Pixels, just pixels.
And then you just did the PCA on all pixels, and then it happened to be a circle when you just rotate it.
Yeah, isn't that cool?
That's weird, right?
Well, it's sort of weird, but it makes sense. I mean, it must tie up because 359 degrees is close to 1 degree. And I guess you could probably reason that it might end up being a circle, but I didn't expect, I thought, I suppose the transformation is a constant transformation, right?
If you sum everything up and define that as the center, you can show that the distance from everything to that center is the same. So it's actually
That's nice. It's a nice way of thinking about it. Yeah. You see? See, he would have known it was going to be a circle. But I didn't. I thought, yeah, that's cool. But yeah, so that's how it looks like. But yeah, that's a good explanation. I like that explanation. So the explanation was, for those of you listening at home, that if you sum everything up and look at the mean, everything's going to be equally distant from that mean, or that's the intuition, therefore it should be a circle. Yeah. Yeah, I'd have to check that, but that would make sense to me. I mean, it must be true given what we see. So in practice, of course, there's other transformations for digits, thinning, translation. But my argument is So this is one of these other arguments where, like, I believe it's true, therefore I say it's true. For data with structure, you expect fewer distortions than dimensions. So what I argue is that if that's not true, then your data is kind of unstructured. But then that becomes my definition of unstructured data. So it's maybe a worthless statement, but that's kind of the way I tend to think of things. So if I expect the data to lie on a low-dimensional manifold, I should say this is not the only way of dealing with high-dimensional data. I think another way, I think this is a really interesting way, another way is to sort of specify conditional independencies between those output dimensions. That is actually this form where you've got a sparse covariance matrix, the thing we saw before. And that's what people do in probabilistic graphical models. And one of the things that interested me was combining these two approaches, and that's actually how deep Gaussian processes came about. But 6-8 years ago or something, when I didn't call them deep Gaussian processes because people weren't calling things deep. Okay, I don't want to talk about spectral approaches. I just want to dive in. There's lots of ways of doing this, and I would normally review them, but in the interest of time, what I want to show is what you can do with Gaussian processes for this problem. I'm going to assume someone else is teaching about dimensionality reduction. So what we'd like to do is a probabilistic nonlinear principal component analysis. Principal component analysis is like the go-to method. Why is it the go-to method? Just like that example we had from the back before, there's like 9 different explanations, or 10 or 12, of what you're trying to do that lead you to principal component analysis. It's a really fundamental thing. So we'd like to sort of generalize that. Turns out that if you try and nonlinearize each of those 9 different explanations, you get a different nonlinear model. So what I'm trying to nonlinearize is probabilistic explanations of PCA, because I want probabilistic models of the data. But it turns out, again, that I'm not nonlinearizing the conical PCA, although it actually took me a while to sort of think about that and realize the implications. So the way we're going to go is I'm going to first of all present a new probabilistic interpretation of PCA. Before I do that, I'm going to even review with you how you can derive probabilistic PCA with your knowledge I've given you. So it's on the next slide, but I'm just thinking live, I'm just making the decision to do this on the board because it's so easy. When I did these derivations, I didn't really know how useful the properties of multivariate Gaussians were. So I didn't do it this way. I did a load of Woodbury formula tricks. But so what I want to say is these are latent variable models. And the way we approach it probabilistically is we say there is some low-dimensional space X, which I don't observe. And this is the control space, like the degree of rotation or the amount of thinning. But I can't see that because I just see the data. So I like very simple graphical models. What I observe is Y. And there's a relation there's a mapping that goes from X to Y. So I see something high dimensional. And we've just looked at one of those mappings. And the mapping we looked at was this one. So each vector Y, so that would be a row vector, is given by a mapping from the X vector. So look, every model turns out to be this. Now, in Kalman filters, so I've done these things the wrong way around, because in the Kalman filter, I said that this is a temporal prior, a Gaussian process, a complicated little thing. In PCA, all you say is that X is sampled from a Gaussian. You don't even give it a scale. And then you say epsilon is sampled from a different Gaussian. Who can tell me, therefore, what the marginal likelihood, so this is each individual data point, I should say. So X is independently sampled, so I could put in here a product over all data points for epsilon I, a product over all data points for X, but I'm just specifying for one data point, and everything's independent anyway. So can someone tell me what the marginal distribution is for Y using the properties of Gaussians I've already told you about? Perfect. It's trivial, isn't it? That's a really nasty integration involving the Woodbury inversion formula if you don't know these. Absolutely perfect. That is the covariance matrix underpinning factor analysis. Well, factor analysis is slightly different because in factor analysis, you allow, sorry, this is a vectorial thing. This is a vector here, multi-outputs. And this is a vector here. So I haven't really, yeah, that's why I've got the I there. So I have represented that. If I make this a diagonal covariance, so each output of that vector has its own independent variance, then trivially, I just get D here, and that's factor analysis. This is PCA. That factor analysis is PCA. Factor analysis is PCA. What's the difference between, well, they're the same bloody model. In fact, it's a bit depressing. If you read Hotelling's original paper on principal component analysis, Pearson did not write about principal component analysis. He wrote about another model that algorithmically is the same as principal component analysis. That's 1901. Hotelling invents the term principal component analysis, and the whole start of his paper says, people have invented this thing called factor analysis in psychology, and I'm going to do it properly. I mean, kind of. And then he goes on to derive PCA. But he says, I don't like the name factor analysis because factor means a specific thing in maths, and and means a different thing in psychology, like the factors affecting you. Sadly, PCA is just a factorization of the covariance matrix. So it was a terrible misnomer to rename it principal component analysis. It should just all be thought of as factor analysis, because whether you believe these factors are psychological factors, they are also factors of the covariance matrix. The psychological factors are factors of the covariance matrix. It's a happy coincidence there. So what a shame they renamed it. And that's, I think, caused no end of confusion and papers read about differences. There is no difference. They're the same model with one's with an isotropic noise and one's a heteroscedastic across the output, a non-isotropic noise model. It turns out that's the model. That's the model. Why is there all this fuss? Well, this, again, the importance between model and algorithm. So actually, Hotelling didn't add this term. So Hotelling's model was precisely that. That's what he described, without the noise. So Tipping and Bishop added that, and Sam Roeis added that in the mid-1990s. So it took 60 years to realize that if you add that term, it doesn't negatively affect things. So that's the sort of machine learning contribution there. And Tipping and Bishop proved that the maximum likelihood solution is the same. So what you really want to do is fit this model, and what you can show is the model fit is that W is the principal eigen vectors of the covariance matrix, which is what the PCA algorithm is. But that's the algorithm. People think of PCA, they say, oh, PCA is when you just take the principal eigenvectors of the covariance matrix. And I hate that, because that's an algorithm, not a model, and PCA was defined as a model. And if you, I mean, lots of models end up with that algorithm, but they're all trying to do different things. Now, what I did sort of to get Gaussian processes into the game was something slightly different. So here, there is actually another term, which is W. And what you would really want to do if you're probabilistic is integrate over W instead. Instead. We don't have to do instead. You'd like to integrate over W as well. But what I did was something slightly different. I did it instead. So now this is not how I derived it. I spent about an hour going through the derivation, copying Mike Tipping's derivation. But what I want to know now is a slightly different model. Same likelihood, but I'm going to write it in a different way. This turns out to be exactly the same likelihood. But here, I'm writing a row of Y. So Y itself, our data, is again a series of rows, and each one of these is a row. Now, on this side, I'm going to give you the vector for the columns of Y. So a column of Y, Y colon, comma, J, yep, that's right, is equal to X, where X is my latent variables, times, got to get this right now, W, I think it's a row of W, plus epsilon J, where if epsilon is J is drawn from a Gaussian with zero mean and covariance sigma squared I, this is actually the same likelihood as that. It's just written describing the rows instead of the, I mean, these things can all be written in terms of individual values. Really, Y is just, Yij is just Xi, comma, colon, transpose Wj, comma, colon, like that. It's just an inner product we're just computing the inner products all at once with the matrix notation. But when one, we're computing all the rows all at once, and the other, we're computing the columns. And the only reason we're writing it like this is because now, instead of putting a prior over X, I'm going to put a prior over W. What's the covariance function now for Y? So what's the marginal distribution for Y? So Y is now XW plus epsilon, and W is drawn from this distribution. So it's just exactly the same operation as that, but what does it look like? So now, and this is the rows of of Y, sorry. The rows of Y are drawn from this. This is going to be for the columns of Y. So this model that turns out to be independent across rows. This model is going to turn out to be independent across columns. So anyone? Y, column, comma, J. What's the mean? 0. The covariance? Yeah, so I've actually popped an alpha in there, so we're going to have alpha x transpose plus sigma squared I. You won't be surprised that the maximum likelihood solution for x in this model is very similar to the maximum likelihood solution for W in this model. The maximum likelihood solution for W is the first Q principal eigenvectors of the covariance matrix. Now, covariance matrices, if the data Y is centered, the covariance matrix, if we defined our design matrix Y in this way, the covariance is given by Y transpose Y, if the data is centered. This model here is solved, you just follow through all the maths, it's going to come up in a minute, by computing the first Q eigenvalues of YY transpose, which is the inner product matrix. Q eigenvectors, sorry. Now, it turns out that those two eigenvalue problems are equivalent, and that you're actually computing the same thing. So this model here turns out to be an alternative formalism of probabilistic PCA. The algorithms turn out to be the same, but the models are different. But there's this weird duality. This is why PCA keeps popping up. X and W always appear in this inner product and only appear in this inner product. So in optimization, that's the sort of thing that leads to duals that you can optimize in two different spaces. And the same type of idea, so this is why I sort of called it dual probabilistic PCA, is going on here. That instead of integrating over X, the unknown latent variables, we're integrating over W, and then we're saying, give me the most likely. So these are the two different approaches. One here is saying, integrate over all possible latent explanations, give me the most likely mapping. And this one here is saying, integrate over all possible mappings and give me the most likely explanation. Yeah? But they both lead to PCA algorithmically. The model is actually different. And this would normally, perhaps the better name of this, which I wasn't aware at the time, would be principal coordinate analysis. It also is sometimes known as classical multidimensional scaling, this type of model. But again, this model is new. But this way of thinking about it is thought of in that way. So what's interesting, though, about this now? Now we've got it in this form where we've integrated over the mappings. What can I replace this relationship with? Kernelized version, yeah, precisely, although as I would like to say it, because I don't like the K word, just a function. And then what I have to say is that this function is a Gaussian process. And actually, then the thing's even more trivial. You don't even need to know the rules. You just need to say, okay, if the covariance function, that is just the covariance function for the linear process. So if the covariance function is K, this is now my model. Oh, wait, that's just a multi-output Gaussian process with independent GPs, because the independence here turns out to be across P. We'll have that, I'll bring that back up now on the slide. All right. So these are the, oh, they're not. Okay, so these are the just definitions of the terms of what we're using, but it's similar to what we've used before. And then this is the important point. This is the model on the right. This is the model graphically for probabilistic PCA. And then this is the same thing for dual probabilistic PCA. So we're now at sort of this point here. So, but what I've included here is the proper independencies. I've written that in a slightly different way to what I wrote here. But this is really interesting because most models are not defined as independent across features. Like I said at the beginning, IID, rubbish, forget it. Okay, but it is useful. I mean, I kind of do that a little bit for effect. This is an IID model here, probabilistic PCA, is IID. It's just a covariance every data point sample. Now, IID, the foundation, and someone said, well, you can prove stuff about IID. So what you can show here, you can show that if your model is genuinely the correct model, like the data was sampled according to this thing I talked about here, that in the limit of infinite data, you will recover the correct parameters. So if you have very large n and small p, then you will recover the correct parameters. And the fact that, in general, like for things like microarrays, you actually have very large p and small n. And there's, oh, large p, small n problem. I mean, it's a ridiculous thing to say, large p, small n problem. Because what it says is that don't go out and collect more data about this thing. I would rather you told me about 7 genes in this person. Don't tell me about 6,000. That's idiotic. It makes no sense to claim that a data set has a large p, small n problem. It means like, if we had, like, so if I sent Philip out into the forest, just there or wherever it is, and said, Philip, you find every animal in the forest. And he said, well, there's only 10. We've killed them all. There's only 10. But I've started finding out characteristics. This animal has wings. This one doesn't. This animal has a beak. This one doesn't. And he starts describing these animals. And he gives me 15 characteristics. I'm like, well, great. There's only 10. No, well, let's say he gives me 2 characteristics. So I'm happy because I've got n is 10 and p is 2. So I'm in my office and analyzing this data. And then Philip comes back in. He says, I was just out on my mountain bike. And I thought, well, there aren't that many animals. But I'm going to collect more features about each of them. And I have a really big list. Now I have 100 features about each animal. And still 10 animals. And I'm like, Philip, you idiot. You have now given me a large p, small n problem. Before I could analyze this data, and now I can't. That is an absurd, stupid, ridiculous thing to say. And the reason people say it is a consequence of proofs about this type of model, that you can show that maximum likelihood is consistent in a large n, small p limit, because parameters don't grow, and data does, and these parameters become better determined. So, if you have large p, small n, here's my advice. You define this model, which has a large n, small p problem. You can show this model is consistent. I mean, these consistency proofs are rubbish. These models aren't correct, right? But if this were the general generative model for the system, you could show that as the data increases in p, so in this case, when Philip comes in, brilliant, Philip, go and collect more, because these x's become better determined as p increases and n stays finite. This model has a large n, small p problem. So you immediately realize when you see this that all these things are not a consequence of the data, they're a consequence of your model and lack of imagination and using IID models. So never accept it when people say curse of dimensionality. It's just rubbish. It doesn't exist. It's just how you, here, the difference is that here we're defining interrelations across n, whereas before we were defining interrelations across p. The right thing to do, neither of these is right. The right thing to do, if we could, is to define interrelations across p and n. And then we would end up like with one parameter. And there would be no p or n problem at all. There would just be how we chose to specify the covariance matrix, which is the real challenge. Few parameters and a good old covariance matrix tell everything how it interrelates. Why don't we do that in practice? Computational reasons. So the GPLVM was this sort of realization, okay, well, let's put a kernel in here. So that's just stuff I've said already. And then just noticing that this is a product of Gaussian processes with a potentially nonlinear covariance function over multiple outputs. And then in the last minute, I want to show you what you can do with that with my favorite, in fact, it's probably linked in here. So people have used this quite widely in the low n large p domain. And this is my favorite video, probably have seen this before. Oh no, the internet doesn't exist. Okay. The internet exists, and I don't even have the thing that allows me to edu-roam. Okay, so this is going to be... I did a lecture in front of a class of 8 to 10-year-olds, and as a careers lecture, and I was billed as an IT lecturer. So, which wouldn't be the way I'd prefer to call myself, but in the lecture, one of the questions, which was my favorite question almost, well, there were lots of really good questions. Where's the networking thing gone? It's working. Okay, we're on. We're on stream. On stream. So just finish the story. One of my favorite questions was, have you ever told anyone to switch it off and switch it on again? Which is what I just did with the Wi-Fi, which triggered the question. And I said, yes. And it's a very good thing to do. Have you ever played Minecraft? And they're like, yeah, we all play Minecraft. And I said, well, you know when you build a world, and then after a while you're like in, what's it called, where you don't die? There's some sort of creative mode. And then you've built all this stuff, and actually you start with a nice world, and you've messed it all up. And now it looks a bit ugly, and then you think, oh, I'll just reset the world and start again. I said, that's what you're doing when you turn it off and turn it on again. And they were like, ah. That's what's happening inside your computer. Okay, so this is a video from a guy called Bill Baxter that is my favorite application of this model that just uses Gaussian processes as those mappings. So that's the trick, right? I didn't actually derive it in this way. I sort of thought, what if I were to use Gaussian processes in that model and just optimize over the inputs? And then later I realized it had this theoretical justification. So Bill was in Japan. He downloaded my original GPLVM code in C++ and fixed a load of bugs and gave it to me back. So that's another good reason to put your code online. And then he did this stuff with it. So all this intro stuff is about the fact that drawing's interesting. And then what he's going to do is he's going to draw 4 faces with slightly different expressions. Now, these are being drawn in lines, and the stuff that I've never read the paper, I just like watching the video, you know, like my kids. But somehow he's taking those lines and converting them into vectors. Now, in order to do that, there's a correspondence issue. So, you can take any line and convert it into a vector, but depending on which way round you drew the line, the vector changes direction. And you need to sort of, for the next drawing, you need to map each line onto the next drawing. So you need to know which vector, how they come up. So there's a correspondence problem there. And that seems to be the most difficult thing about this thing, because when he fits the model, he has an approximation to the correspondence problem, he doesn't get it right. So he's drawing, so this is like data, this is Y, and then he's going to fit the model. He's got this thing on the left, learn first, learn better, learn best. And he's going to fit the model now. I think those are the 4 data points. So N is 4, P is whatever the dimensionality of these encodings of the lines. And then he's going to show the 2-dimensional space here. You see the crosses in the 2D space? That's the 2-dimensional latent space. And now he's moving around in that latent space, and he's showing us the mean function of the Gaussian process, which is a sort of trick I've used to explain these models. But because the correspondence doesn't work, some of those lines go, whoop, whoop. They move in kind of interesting ways. But he's just going to tell it, okay, look, that line's really connected to that line, and this is that way around. So there's a problem with the nose, I think, now that the nose, one of the noses is mapped the other way around. So still something happens funny with the nose. You see the nose crosses over itself? Yeah? But in a natural way. This is a nonlinear model in probably hundreds or so dimensions with 4 data points. P is like 100 and something. The model is nonlinear, and N is 4. But these 4 N are very well determined because of the high dimensionality of the problem. So actually, this is probably a very good model of the data, about as bad as you can do. But now look, he can now sort of get the face to make different interpolated expressions, none of which are really part of the original model. This is why I believe that in the end, Gaussian processes will win through. Because this type of transformation is extremely complicated and easy for humans to do, though. It's not that this is hard. A kid could draw that for you if they've got the drawing skills. Question?
So, if the nonlinear, like this extraction of feature is a nonlinear thing, apparently, right? So why not just PCA? Like, why do we even care about any probability?
Well, PCA would be awful. It would do a horrible interpolation. It would look at all those 4 points and then just try and draw the best fit line through them. So conceptually, what's sort of going on here is, yeah, it's nonlinear, but really all it says, if you think about the sort of what the function would do in these high dimensional spaces, it would just interpolate smoothly between the 2 different points and try and find a configuration where that smooth interpolation is most likely. So it's really about the configuration of the latent points and how they interrelate. And then you need a nonlinear interpolation. So here he's doing insects, which is even weirder.
Okay, I think I asked more after.
Sure. So one, of course, it doesn't know about constraints. So you'll see the legs. If you watch carefully on the legs, they'll fall off the side of the body a little bit and come back on. Actually, my favorite bit is at the end, he actually has a sort of, I was listening to Kraftwerk this morning. I think when you're in Germany, you should listen to Kraftwerk. No, not now. But he's got some sort of cool music at the end. So he makes the whole thing, where's the full screen thing?
You can also connect the audio cable.
So the annoying thing about this work is, of course, people who, so in this thing he's doing a probabilistic, you connect the microphone thing. Yeah, it's not that exciting. I could try it, yeah. It's probably going to come out really loud now that I put the volume up. But the, this is his probabilistic stamping tool. So now he's just sampling some random place in the latent space, creating a different insect. You can see how useful this might be for, like, you know, animation and these sort of things. This works 2006, and I think one problem is people just don't understand how he managed to do it. I don't know. I mean, there was this point in the financial crisis when I thought I might have to quit my job, you know, and just find out. If I started thinking, well, what would I do in the real world? And I thought, I'd just implement an app with this on it. People would love it. I don't know. You know, it should extend to ARM. So, oh no, it's not coming through with the music. Oh yeah, here we go. So it's just, you submit this to a conference. You know, who wouldn't do graphics? Just making insects dance. That's why you should work on Gaussian processes. And that's my time out.